And let's locate some charge somewhere in space, let's say here. Let's put a little charge Q over there. And let's say that when I place this test charge at this initial location, right, that charge is going to move some way. It's going to have some path. And sometime later, I'm going to find that charge at location F. So the initial point is this one, the final point is over there, and the particle moves following that path. And it moves only under the action of the electric field present at that location in space. So I'm going to describe the location of that particle with some axis, with some coordinate axis, and the initial position is a vector SI, and the final location is a vector SF. So what I'm starting to consider right now is what is the change in the potential energy of that charge as it moves from I, the initial point, to the final point. Let's start with that consideration. And that's going to give us the connection between the electric field and the electric potential. Okay? So what is the change in the potential energy when that charge moves that way? So the change in the potential energy, electric potential energy of the charge, is equal to the negative of the work done by the electric forces. Those are the only forces doing work in this problem. The charge is moving by because of the electric field acting on it. And that work has been done when you move from the location I to the location F. This is the negative of the integral of the force. The electric force acting on that charge, dot product with the displacement vector. The displacement vector points along the path that the particle followed. Right? So this is going to be equal to the integral between SI and SF. Should not be forgetting the minus sign out here. And the electric charge is Q times the electric field. Right? Times dotted with ds. So what do we have here? The Q, we can pull it out, and this is the integral of the electric field ds. This is the change in the electric potential energy of that charge. Right? The change in the potential in the potential energy of the charge is related to the change in potential. Right? The connection is just through the charge. So remember that the potential is equal to Q times the potential energy is equal to Q times the electric potential. So that means that if I divide this, the change in the potential energy of the particle when moved between those 2 points, if I divide it by the charge, that should give me the change in the potential that that particle experienced when going from I to F. Right? So the change in the potential will be, according to that expression over there, the integral of the electric field along the path that you follow. So if you know the electric field in all points in space, and you move from, you know that the particle moved from point I to point F, you know through what difference in potential that particle moved. Right? This is what this equation is telling you. The difference in potential between the final point and the initial point, potential at the final point minus the potential at the initial point, is this number, the integral of E times ds. So E is a vector quantity. If you dot it with the vector ds that describes the path, you would end up with a scalar quantity with the difference between the potential at those 2 points, those 2 locations in space. So I'm going to write that again over here. Delta V equals minus integral of E dot ds, and that's between some initial point and some final point.
Now let's look at a simple case where the electric field is constant. So this is the case of a capacitor, the electric field inside a capacitor between the 2 plates. So if the electric field is constant, and let's say that the electric field points from left to right, given by these red arrows, parallel because it's constant, then what does this integral give us? Well, if we're moving from some initial point I to some final point F, and the displacement vector delta S points in that direction, then we can talk about the component of delta S that is parallel to the electric field, to the red arrows, and the component of the displacement delta S that is perpendicular. These two components are important to identify because there is a dot product in the integral, the dot product between E and ds. So that means that only the parallel component of the displacement makes a contribution. Now in the integral, we can pull out the electric field because it is a constant. In the case of constant electric field, we end up with a delta V that is equal to minus E times the integral of ds between Si and Sf, that is delta S, the vector that goes from the initial to the final point. So our delta V is simply minus E times delta S, dot product. So let's use this expression for the case when the displacement of the particle is parallel to the electric field. So that is, if the initial point and the final point are along the x direction, along the direction of the electric field. Since E and delta S point in the same direction, the cosine of the angle between them is a positive number. In the case where they're parallel, the angle will be 0, so the cosine will be 1. So delta V is negative E times delta S. So that means that the potential decreases as you go from the initial point to the final point. The potential at the final point is less than the potential at the initial point. The opposite situation is when the delta S vector points in a direction opposite to the electric field. So you're not moving in the direction of the electric field, you're moving opposite to the direction to the electric field. So you're going uphill, or upstream if you want. So in that case, delta V has a minus, but now E dot delta S is a negative number because the cosine of 180 is minus 1. So that minus 1 with the minus 1 outside cancels, and delta V is a positive number. It's equal to the magnitude of E, magnitude of delta S. The fact that delta V is positive means that as you move along delta S from the initial to the final, your potential is increasing. So your final potential is bigger than your initial potential.